For decades, the promise of fusion energy has tantalized the world. Fusion, the process powering the sun, offers a nearly limitless source of clean energy. Yet, something has changed. A wave of investment is pouring into fusion startups driven by significant progress in overcoming technical challenges. The origins of the "fusion is always 50 years away" prediction can be traced back to the early days of fusion research. Initial optimism led to overly ambitious projections, but the challenges were formidable. Containing a superheated plasma within a magnetic field proved far more intricate than anticipated. The history of fusion energy research is replete with ambitious projects that encountered unforeseen technical challenges. ITER, the International Thermonuclear Experimental Reactor, exemplifies this pattern with numerous delays and cost overruns. However, these delays reflect the inherent complexity of fusion science and engineering. Despite historical baggage, a palpable shift in perspective is underway. Advances in material science, supercomputing, and diagnostic tools have significantly de-risked fusion research. Fusion, with its potential to provide carbon-free energy, has emerged as a compelling long-term solution to climate change. Taming the unruly plasma. Advancements in confinement. Scientists have made remarkable strides in understanding and controlling plasma behavior. Tokamaks and stellarators have undergone significant design refinements, improving plasma stability and confinement. Superconductivity, the backbone of fusion reactors. Superconducting magnets offer significant advantages over conventional electromagnets, requiring far less energy to operate. ITER will utilize niobium tin and niobium titanium superconducting magnets, generating a combined magnetic field strength of over 11 teslas. Energy input. Igniting the fusion fire. Initiating and sustaining a fusion reaction requires heating the plasma to temperatures exceeding millions of degrees Celsius. Scientists employ auxiliary heating methods, such as neutral beam injection and radio frequency heating, to achieve higher temperatures. Diagnostics and control. Unveiling the secrets of plasma. Fusion researchers rely on a vast array of diagnostic tools to monitor the plasma's temperature, density, pressure, and magnetic field. These diagnostics are fed into sophisticated control systems that adjust reactor parameters in real time to maintain plasma stability. Inertial confinement, compressing towards ignition. Inertial confinement fusion seeks to replicate the intense conditions found at the heart of stars by compressing a tiny pellet of fusion fuel. The National Ignition Facility achieved a historic milestone by demonstrating net energy gain from an inertial confinement fusion reaction. Magnetic confinement, trapping a star in a bottle. Magnetic confinement fusion relies on powerful magnetic fields to contain and control the superheated plasma within a reactor. This approach aims to create a stable and long-lasting plasma within a magnetic bottle. Tokamaks, the leading contender. The tokamak, a donut-shaped fusion reactor, has emerged as the leading contender in the pursuit of magnetic confinement fusion. ITER aims to demonstrate the feasibility of fusion power by producing 500 megawatts of fusion power for extended periods. Section 4. Stellarators, the twisted alternative. While tokamaks have long dominated the fusion landscape, stellarators, with their intricate and twisted magnetic field geometries, offer a compelling alternative. Imagine a fusion reactor that resembles a work of art. Its complex coils twisting and turning in space, creating a magnetic field that seems to defy intuition. This is the essence of a stellarator, a fusion device that promises enhanced plasma stability and steady-state operation. Unlike tokamaks, which rely on a combination of external coils and a plasma current to create the confining magnetic field, stellarators generate their entire magnetic field using a set of intricately shaped external coils. These coils are carefully designed to create a three-dimensional magnetic field that twists and turns, forming a series of nested magnetic surfaces that confine the plasma. This inherent three-dimensional nature of the stellarator's magnetic field provides several advantages over the tokamak's simpler two-dimensional field. The more complex field geometry of the stellarator eliminates the need for a plasma current to maintain stability, simplifying reactor operation, and potentially enabling continuous, steady-state fusion reactions. While stellarators have historically faced challenges in terms of their complex coil designs and manufacturing, advancements in computer modeling, materials, science, and manufacturing techniques have made their construction more feasible. As research and development continue, stellarators hold the promise of becoming a viable and potentially superior alternative to tokamaks in the quest for fusion energy. Section 1. The first wall. A balancing act of resilience. The reactor wall, particularly the first wall facing the scorching plasma, is the unsung hero of the fusion reactor. Imagine a barrier thinner than your fingernail containing a miniature sun. It must withstand relentless heat, radiation, and energetic particles. The plasma radiates intense heat, primarily in the form of X-rays. This can quickly melt or vaporize conventional materials. The first wall also contends with high-energy neutron bombardment. This causes material degradation, embrittlement, and swelling. Designing a material to withstand these conditions is a formidable challenge. Neutrons, the subatomic particles that hold the nucleus together, are essential for sustaining the fusion reaction by breeding tritium, a crucial fuel component. However, these very same neutrons pose one of the most significant challenges to the longevity and efficiency of fusion reactors. As neutrons escape the plasma, they collide with the atoms in the first wall, transferring their energy and momentum. These collisions can displace atoms from their lattice positions, creating defects within the material. Over time, these defects accumulate, causing the material to swell, become brittle, and lose its structural integrity. This neutron-induced damage can significantly shorten the lifespan of the first wall, leading to costly and time-consuming replacements. Furthermore, neutron bombardment can transmute atoms within the first wall, transforming them into different elements. Some of these transmutation products can be radioactive, posing handling and disposal challenges. The accumulation of radioactive isotopes within the first wall also contributes to the overall activation of the reactor, making maintenance and decommissioning more complex. Minimizing neutron damage is paramount for the success of fusion energy. Researchers are exploring various strategies, including developing new materials with higher resistance to neutron damage, optimizing the geometry of the first wall to reduce neutron flux, and exploring innovative concepts such as liquid walls that can continuously replenish themselves and mitigate the effects of neutron bombardment. Tritium, a heavy isotope of hydrogen, is a crucial fuel for fusion reactions, but it is not naturally found in significant quantities on Earth. This scarcity necessitates breeding tritium within the fusion reactor itself, adding another layer of complexity to the challenges faced by the reactor wall. The most common method for tritium breeding involves using lithium, a light metal, as a neutron absorber. When a neutron strikes a lithium atom, it can split the lithium nucleus, producing tritium and helium. This reaction, known as the lithium-neutron reaction, is essential for maintaining a sustainable fuel cycle within the fusion reactor. To facilitate tritium breeding, a dedicated breeding blanket containing lithium is typically incorporated into the reactor wall design. This blanket surrounds the plasma, capturing escaping neutrons and maximizing the tritium production rate. However, designing an efficient breeding blanket poses several challenges. The breeding blanket must be carefully designed to balance neutron absorption for tritium production with neutron moderation to prevent damage to other reactor components. The lithium within the blanket must be chemically and thermally stable at high temperatures and under intense neutron irradiation. Furthermore, efficient extraction and processing of the bred tritium are crucial for maintaining a continuous fuel supply. Maintaining the purity of the plasma is paramount for achieving and sustaining efficient fusion reactions. However, the intense conditions within the reactor can lead to material erosion from the first wall. releasing impurities into the plasma and degrading its performance. One of the primary mechanisms for material erosion is sputtering, where high-energy particles from the plasma collide with the first wall, knocking atoms loose from the surface. These sputtered atoms can then enter the plasma, where they become ionized and radiate energy, cooling the plasma and reducing fusion efficiency. The choice of first-wall material plays a crucial role in minimizing sputtering. Materials with high sputtering yields, such as carbon-based materials, can lead to significant plasma contamination and reduce reactor performance. Tungsten, with its high sputtering resistance, has emerged as a leading candidate for first-wall applications. In addition to sputtering, other erosion mechanisms such as evaporation, melting, and chemical erosion can also contribute to plasma contamination. Minimizing these erosion processes requires careful selection of materials, optimization of plasma-facing components, and development of innovative solutions such as liquid walls or diverters that can handle high heat and particle fluxes. In the quest for a material capable of withstanding the inferno within a fusion reactor, tungsten stands out as a formidable contender. Imagine a metal so dense it feels heavier than it looks, able to withstand temperatures that would vaporize most other materials. This remarkable resilience makes tungsten a prime candidate for the first wall of fusion reactors. Its high melting point, exceeding 3,400 degrees Celsius, allows it to endure the intense heat flux from the plasma without melting or deforming. This inherent robustness ensures the structural integrity of the reactor, a critical factor for safe and reliable operation. Beyond its thermal fortitude, tungsten also exhibits exceptional resistance to sputtering. The constant bombardment of high-energy particles from the plasma can chip away at the first wall, releasing impurities that can contaminate the plasma and degrade its performance. Tungsten, with its strong atomic bonds, holds its ground against this onslaught, minimizing the release of sputtered atoms. This low sputtering yield makes tungsten a desirable choice for maintaining plasma purity and maximizing fusion efficiency. Furthermore, tungsten's high atomic number, a measure of the number of protons in its nucleus, contributes to its ability to absorb neutrons, the energetic particles that drive tritium breeding. While neutron absorption is crucial for sustaining the fuel cycle, excessive neutron irradiation can damage the first wall, leading to material degradation and shortening its lifespan. Tungsten's neutron absorption capacity helps to moderate this damage, extending the operational life of the first wall and reducing the frequency of costly replacements. This combination of high melting point, low sputtering yield, and neutron absorption capacity has made tungsten a favored choice for first-wall applications in fusion reactors. Beryllium, a lightweight and versatile metal, is a potential contender for the first wall of fusion reactors. Its low atomic number and excellent thermal conductivity make it promising. However, beryllium erodes rapidly under particle bombardment, requiring frequent replacements. Section 3. ITER's Material Choice Balancing Trade-Offs. ITER, the world's largest fusion project, faced a dilemma: beryllium or tungsten for the first wall. Beryllium offered low radiative losses but had safety concerns. Tungsten, though with higher radiative losses, proved more durable and safer. The choice of tungsten highlights the complex trade-offs in fusion reactor material selection. Section 4. Beyond tungsten and beryllium. Exploring the frontier. While tungsten and beryllium have emerged as the frontrunners in the quest for the ideal first-wall material, the search for even better solutions continues. Material scientists are pushing the boundaries of material science, exploring novel alloys, composites, and entirely new classes of materials with the potential to revolutionize fusion reactor design. One promising avenue of research is the development of high-entropy alloys, a new class of materials that incorporate 5 or more elements in near-equal proportions. These alloys exhibit exceptional strength, ductility, and radiation resistance, making them attractive candidates for extreme environments like those found inside fusion reactors. Another area of exploration is the use of liquid walls, where a thin film of molten metal such as lithium or tin flows over the inner surface of the reactor. Liquid walls offer the potential to self-heal from damage, continuously replenish themselves, and even extract heat and breed tritium more efficiently. As research and development continue, we can expect to see even more innovative materials and designs emerge, pushing the boundaries of what's possible and bringing us closer to a future powered by the promise of fusion energy. The quest for the ultimate fusion reactor wall is a testament to human ingenuity and our unwavering determination to unlock the power of the stars. Section 1. The Dawn of a New Energy Era. The pursuit of fusion energy is a testament to human ambition, our relentless drive to harness the universe's power for humankind. Fusion has lingered on the horizon, a tantalizing promise just out of reach. Yet the landscape of fusion research is transforming. Scientific breakthroughs and technological advancements are breathing new life into this endeavor. The 50 years away adage is giving way to optimism. Ingenious solutions are meeting the challenges of fusion energy. New materials are being developed to withstand extreme conditions. Investment from governments and private enterprises is growing. Fusion startups are racing to unlock the power of the stars. The path to practical fusion power has hurdles. Recent progress provides ample reason for optimism. We are on the cusp of a new energy era where fusion could fuel our future. Section 2. Fusion, a shared future for humanity. Fusion energy holds the potential to address some of the most pressing challenges facing humanity. Climate change, driven by fossil fuels, poses an existential threat to our planet. Fusion offers clean, safe, and virtually limitless energy. Unlike fossil fuels, fusion produces no greenhouse gases. Its byproducts, helium and neutrons, pose minimal environmental risks. Fusion reactors are inherently safe. Fusion reactions are self-limiting, preventing meltdowns. Disruptions lead to rapid cooling, extinguishing the reaction. This eliminates the risk of catastrophic accidents. Fusion energy offers energy independence and security. Fusion-fueled deuterium and lithium is abundant and widely distributed. This reduces reliance on geopolitical hotspots. Fusion is a shared human endeavor requiring international collaboration. It demands unwavering commitment and belief in our collective ability. The rewards are a cleaner, safer, and more sustainable future. Let us embrace the challenges ahead with optimism and a shared vision for a brighter future powered by the stars.